Today I'm going to start my next sessions on piezoelectric transducers. Okay, in my last class, I have covered some other type of transducers like you can say like that capacitive, inductive transducer, capacitive transducers. Okay, means variable that it will work with the variations of that inductance and the capacitance. I am discussing about piezoelectric transducers. Okay, so in piezoelectric transducer, I know that you know that what do you mean by that piezoelectric effect. Okay, means if you using some of the crystal. Okay, so piezoelectric crystal. So if some force is applied to that crystal, so both side you can see that force is applied to the crystal, so you will get some output voltage. Okay, so output voltage across the crystals. Okay, so here you can see that width, okay, sorry, the thickness of that piezoelectric crystal is T is given, force F is here. Okay, so what will be your output voltage? As per that convention, it is written that E equal to it should be the GTP. Okay, so it depends upon your pressure. Okay, so what is written that certain material, okay, like certain material, you know, some I think quartz is an example of a piezoelectric material. Okay, so let's check. Okay, so is it example of a physical material or not? Okay, so some material can provide an electrical potentials. Okay, electrical potential when subject to mechanical strain, or conversely can change the dimensions of the subject when subject to be voltage. This effect called piezoelectric effects means some crystals are there. If you provide some mechanical force, means applied across that metal, across that sensor or transducer, means crystal, so you can say like that you will get some of the output voltage. Okay, so from the figure, that figure you can show that piezoelectric crystal placed between two plate of electrodes. So that crystal is there in between two plates. Okay, so it is placed in between two plates of electrode. When force, okay, and that force you have applied. Okay, so force F is applied to the plates. Okay, that electrodes are there, so that force is applied to the plates. A stress will be produced in the crystal. Okay, and corresponding the deformations. Okay, so some force is applied to the crystal means it may cause for some of the deformations of the dimension of that crystal, and due to it tends to try change the dimension of the crystal. That's why there is an effects. Okay, so there is an effects for there is an effects to produce. Okay, that may reason for producing some induced EMF. Sorry, that EMF appeared across the plate. Okay, that induced charge. Okay, so that Q equal to D into F, where the D is the piezoelectric constant. Okay, the output voltage, that your output voltage E equal to GTP. Okay, so T is your thickness of the crystal, P is your impressed pressure, and G is called the voltage sensitivity given by D by E. Okay, so how much voltage sensitivity is there? E is being the strain. Okay, due to the pressure, some voltage will be developed. Okay, and that voltage is responsible for generating that induced that EMF E. Okay, so in piezoelectric metal, okay, so you can say like that quartz. So that jelly salts. Okay, that means in chemical name is that potassium sodium tetrate. Okay, so that which are the example of that piezoelectric materials. Okay, that ammonium dihydrogen phosphates and ordinary, these all are the example of the piezoelectric materials. So that different right now that different instruments, maybe device are designed, okay, based on the piezoelectric materials. Okay, that desirable property. Okay, the desirable properties are stability, high output, intensity, insensitively or to temperature and humidity, ability to form into the desired shape. Okay, these all are the most important features of that material. Okay, so here you can see different application with your metal names. So quartz is most suitable in is used in electronic oscillators. Okay, so it is used for that electronic oscillators, and its output is low but stable. Okay, low but stable means constant output you will getting. That's why quartz is most acceptable. Okay, in normal electrical networks. Okay, then Rochelli salt. Okay, it provides the highest output, so that's why it is quite costlier compared to the quartz metal, but require the protections from the moisture and air, cannot use for the beyond the 45 degrees centigrade, so it having some limitations. Okay, then barium titrate, barium titanate. So it's a polycrystalline. Okay, polycrystalline as it can be formed into the variety of the size and shapes. Okay, that is different properties. Okay, so piezoelectric transducers are used to measure the surface roughness. Okay, surface roughness, strain, force and torque, pressure, motion and noise. This all will be maintained by that piezoelectric materials. Okay, that you should keep in your mind. Okay, then piezoelectric transducers. Okay, so all are the examples of the piezoelectric transducers that I am telling right now. Okay, sorry, it is photoelectric, not like piezo. Sorry for that. It is photoelectric transducer. So photosensitive material will be there. Okay, so that anode and cathode two electrodes will be mentioned, and that maintained and designed by the photosensitive material. So due to the emitting of any light, okay, that may cause for movement of the electrons. Okay, if that movement of the electrons, okay, and that is responsible for developing some electrical signal. Okay, so a phototransducer means photoelectric transducer convert the light beam. Okay, so convert the light beam into a usable electric signal. Okay, into a usable electric signal as shown in, okay, that figure is there. Light strikes, okay, light strikes to the photoemittive cathode and release photoemittive cathode and releases the electron, that I am telling you now. So that photo effective cathodes is there, so that may cause for movement of the electrons from one electrode to another electrode. Current will be reverse directions electron, okay, which attracted towards the anode, therefore the producing an electric current in the circuit. The cathode and the anode are enclosed in a glass of quartz envelope, which is either evacuated to fill of the inert gas. So why inert gas? Okay, so if inert gas is not there, so there is a unwanted aging. Okay, unwanted aging of your cathode means electrons are flowing like that way. So if inert gas is not there, normal gas is there, so it will be directly chemical combinations. Okay, so some chemical changes of your cathode, okay, that may cause for some chemical changes, means combinations with some gaseous material available in your photodiode, okay, sorry, photosensitive transducer, that may affects, okay, and that may accelerate the aging of your cathode. That's why inert gas must be there. Okay, so it should not be reactions with moistures, okay, with moisture and other gaseous component available in the environment or the air. Okay, that's why inert, you should fill that chamber with some inert gas. Okay, that photoelectric sensitivity given by I equal to S into phi. So S is equal to sensitivity, phi is the illumination of the cathode. Okay, illumination means it's a measuring parameter, so how much illumination is available. Okay, so packet of photons are available due to the sunlight. Maybe you are using any other illuminating beams, means light beams, so the illumination is another important features. And I equal to what? It is photoelectric currents. Okay, so current level is very low comparatively the normal currents. Okay, the response photoelectric tubes different wavelengths is influenced by the transmissions of the transmission characteristics, okay, transmission characteristics of the glass tube envelope, okay, that glass tube envelope characteristics means that how fast it is electrons are moving, that depends that current flow rate, okay. Photo emission characteristics of the cathode material, that I'm telling you. So which type of material you are using for designing the cathode, okay, so that decide the efficiency of that photo emissions, okay. So photoelectric tubes are useful for counting purposes through the periodic interruptions of the light source, okay. So you can give sometimes interruptions to the light source, so that having quite effects, okay, that having some effects to that continuing process, okay, counting process, okay. So I think all of you are able to understand that if that discontinuation is there, so definitely there is some interruption with the continuous flow of current, okay. Then photoconductive transducers, okay. So photoconductive transducers means the principle of this transducer is when the light strikes on the semiconductor materials, okay. So previous one is there, that photoconductive, that was photoelectric transistor, that you are using some cathode, okay. So photoeffective cathode means that cathode having some effects on the presence of sunlight or maybe any light beam, okay. Here you are using some semiconductor, okay. So that light is directly, okay, that light is directly coming to that semiconductor, okay. So that semiconductor plate is there, okay, semiconductor film is there, okay, that current is coming, so semiconductor material is there, okay. It is your ammeter, okay, ammeter is there, and its resistance decreases, thereby the producing an increase in the current, okay. The figure shows a cadmium sulfide semiconductor material to which a voltage is applied, okay, that voltage is applied when the light strike, and increase in current indicated by the meter, okay, means light is striking that one, so that way that semiconductor device that you are using the semiconductor film, okay, that is sensitive with the light beam, okay. Due to the sensitivity of the light beam, light is there, so that may cause for changing the resistive path of that semiconductor film, okay. So if the resistive path has changed, then there is a continuations of flowing of electron, okay. If the continuation of flowing of electrons is there, okay, so that may be responsible of what, that may be responsible of movement of that electrons, okay, and the holes, that may be responsible for current flow through this path, okay. So photoconductive transducers, okay, so photoconductive transducers are used to measure the radiations, okay, used to measure the radiations at all wavelengths, okay, all the wavelengths are there, but extreme experimental difficulties are encountered when operating with long wavelength radiations, okay. So it having some limitations, okay. So as per the specification, you have to design your devices, okay. So then we can go for next one, that is your digital transducer. Digital transducer, that concept is it is not specifically, you cannot say like that it's a photo transducer, it's a piezoelectric transducer, it's a variable inductive transducer. Any of the transducer can be converted in the mode of digital transducers, okay. So there is no such limitations, okay. So you can convert it, okay. So what you need to do in digital transducer, so if you have any kinds of continuous signal, okay, with you, so if you have any continuous signal, so you can directly convert, okay, you can directly convert that signal, okay, that continuous signal to the digital signal, okay. So how to convert it, simple thing. So here you can see that one common term is there, means in our electronics field, okay, that is called optoisolator, okay. Optoisolator means you can say like that optical isolations is there, okay. If there is some LED in that optoisolator section, some number, batch number is in MCT2E, okay. In this optoisolator, what happen, if any current is responsible for a LED blinking, okay, current is flowing through this optoisolator, so LED will be blinking, and that LED responsible for emitting some light, and that light will trigger, okay, that light will trigger the base, okay, the base of that BJT. Okay, one BJT will be there. Here you can see that light emitting diode is there, and there is some obstacle. Okay, so it is coming to the detector, so that base is there. Okay, so it is base, emitter, and upper one is collector. Okay, normally we are using common emitter configuration. I know that all of you know about to this concept. So why we are using common emitter configuration, I think that will be discussed in your analog electronics class. Okay, so I am not going to discuss the same thing, but special normal cases we are using CE configurations. Okay, so here that controlling unit is coming to the base of that phototransistor. What type of transistor it is? It is called phototransistor. So it is current is flowing through this path. Okay, so if the D slot is there, okay, so if the shaft is rotating, okay, if the shaft is rotating, so that may responsible for rotating of the disc. Okay, if the disc is rotating, then what happen? If disc is rotating means that current, okay, that current will flowing, okay, that current will flowing through this path. Okay, sorry, this is rotating means there is some obstacle, so there is some obstacle, so when that obstacle is there, okay, there will be no current flowing in this path. Okay, so why? Basically obstacle means the light is not reaching to that photosensitive base of this transistor. Okay, when it is passing, able to pass that light, okay, then what happened? Then you are getting some signal over there, so we will get some discretized signal. So discretized signal means if you convert that continuous signal in the discretized form, means on switch you are adding with your continuous signal, means when switch is on you will get some signal response, when switch is off you will not the response. So as per the switch on instant, means switch on, switch off, switch on, switch off, like that way, so you can get that value. Okay, so that's why you can convert, okay, you can convert that continuous signal to the discretized signal. Okay, so that is your output, it is your output, and it's your time. Okay, so signal is there, okay, continuous signal is there, it is your on and off. Okay, so when it will be on, for the moment of that operation, so you will get some spike. Okay, you can say like that, it's an impulse type response. Okay, and that on time and off time in between that time period is decided by your sampler, means which is responsible, that sampler means that sampling switch which is responsible for converting your continuous signal to the discretized form. Okay, so here you can see some digital counter is there. Okay, digital counter is there, that is responsible for, it is called digital light sensor. Okay, so that is responsible for storing that value and display. Okay, so which dimension what you want for decimal, if you want for binary, so as per your requirement. Okay, so that display will be there as per your processing unit. Okay, so storing the value. So another important feature is that in between impulse to impulse, that how much variation is there. Okay, if that variation is more, then it will be problematic, so most of data may be lost. Okay, so that most of the data may be lost. Okay, so to that selection of the sampler frequency, another important issues. Okay, so you have to select that optimal one, so data should not be lost more, and counter are working fine, like that one. Okay, so then we can go for some Hall effect sensor. Hall effect sensors means you can say like that LEM sensor we are using in our labs. Okay, so it is Hall effect means due to the magnetic fields difference. Okay, so that output will be electrical output. Okay, sensor or transducer you can say like that, but it changes, like it comes from that due to the changes of magnetic field. Okay, that's why it is called Hall effect sensor. So normally it was developed by Edwin Hall in 1879. That's why it is called Hall effect sensor. Okay, that affects, okay, changing of the magnetic fields, okay, in a sensor, and it is responsible for voltage. Okay, so it's a transducer, example of a transducer. Okay, so used for provide the non-contact means to detect measure the magnetic field. Okay, so normally it is providing you the isolations. Okay, magnetic isolation. So optical sensor are there, that is used for optical isolation. So it is magnetic isolation, provide the magnetic isolations, means all sensors. Okay, so directly we can use, okay, so optical and Hall effect sensors, these two sensors were directly connected to our electrical circuit. That's why these two are very well known instead of your quads. Okay, quad means you should provide some mechanical modes, na, strain gauge, quads, all the cases output may be electrical. Okay, so you can using some any of the measuring instruments. Okay, any of the electrical and electronics measuring instrument, there is no problem, but application field. Okay, so initially that before your piezoelectric, okay, so up to piezoelectric, you can see that input is your mechanical, okay, mechanical energy, okay, not like magnetic energy or the electrical energy. Okay, so mechanical. Okay, that's why that is much more famous in the mechanical field. But in case of Hall effect sensor, maybe photo sensors, all are the electrical energy, that in input side. Okay, so that's why these sensors are so much popular in our electrical engineering field. Normally this type of sensors we are using for the purpose of your electrical isolations. Okay, and your electrical isolations, and you can say like that, in the form of optically and the magnetically. Okay, so how to work. Okay, so that common, its working principle is common to us, that presence of that magnetic field is there. Okay, so deflect the electrons flowing through that conductive materials. Okay, that you can see the description of the principle of the Hall effect sensors. Okay, so you can see that north pole and south pole is there, basic DC machines application like that. So you can see that magnets, that lines of force are going from north pole to south pole. Okay, you can see that lines of force are there, and here you can see that electrons moves at the end of the conductive materials, that due to the passing, that cross sectional area is there. Okay, so that metal is there. Okay, so that's cross sectional area. So cutting of flux that may reduce, sorry, that cutting of flux that may cause for induced EMF. Okay, end of the conductive material, and potential is developing in the directions of the perpendicular to the gross current flow. Okay, so definitely that magnetic field is perpendicular with your current flow through this material. Okay, that potential indicate the strength of the magnetic field. So how you can say like that, your strength is comparatively more in normal conditions, so definitely that induced EMF will be more. Okay, that's the basic concept. Okay, so I think I need to check the time. Okay, so time is almost your exam time, so I have to take that attendance, then we can use it. So here you can see some of the applications of Hall effect sensors, means where we are observing that sensor. So like you can say IC engine. Okay, IC engine, electronics ignition systems. Okay, used to determine the positions of the clamp shaft. Okay, applications. Brushless DC motor control, the sensor determination positions of the permanent magnet rotor. So the application of BLDC motor means you are using it in commonly electric vehicles, maybe two-wheeler, three-wheeler, four-wheeler. Okay, so we are normally using BLDC motor. Okay, so special type of motor it is. Okay, and assembly lines. Okay, determine the shaft positions and the velocity. Okay, as contactless limit switches. Okay, so different limit switches are there. Current sensing ICs. Okay, so electrically isolated alternative shunt resistors are there. Okay, so from where we can get this one. Okay, so we are applying that type of Hall effect sensor. So right now I am conclude my today's session. So tomorrow again I have some class, so I can conclude my last module and last class on tomorrow based on that sensor and transducer, and I can conclude the syllabus. Okay, so just wait, actually tomorrow we have also conducting one discussion period. Okay, so actually tomorrow again we'll take some maybe 1.5 hour class. Okay, that class may be started like our previous week. maybe 12:50, maybe 12:30. Okay, so I am not decided right now. So okay, maybe there. Okay, so I have to conclude that portions, and then after that we can have some discussion session. Okay. So if you have any confusion, you can note it down. Okay, so you can note it down, so we can discuss in my next sorry we can discuss to my next class. Okay, thank you all of you. So right